we are going to talk about example 13, the integrations of an fractional function with an repeated linear factors in the denominator. We first explain how the partial fractions in example 13 can be decomposed into the corresponding partial fraction terms. Let us write Rx to represent the integrand. The integrand Rx comprises of an x plus 2 linear factor, but the linear factor is repeated twice. According to the rules, the functions has to be broken down into two partial fraction terms. The first partial fraction term is x plus 2, whereas the second partial fraction term is x plus 2 squared. For each of the partial fractions, you assign a constant a and b to its corresponding numerator. That is how the partial fractions decomposition is done for the linear functions of R, where it contains an linear factors which is repeated. Once the functions R is decomposed into partial fractions, the integrations can then be performed quite straightforwardly in the following manner. That is, the integrations of the fractional function can be performed by summing up the integrations of the corresponding partial fraction term. The integrations of the a terms give you a logarithmic of x plus 2, whereas the b term could be done simply by using substitution rule. Y equals to x plus 2. This integration can then be written as dy over y squared, because dy is just equals to dx according to this substitution. So the integrations of the b term turns out to be simply b over x plus 2. This integration is simply equals to b over x plus 2 with a minus sign. In the following, we are going to explain how the values of the constant a and b in the partial fractions are calculated. In order to find out what a and b is, we will write down the partial fractions into the form which has a common denominator. This could be achieved by multiplying the constant term a with x plus 2. The b terms is left as it is. The next thing to do is to try to equate the coefficients of x and the terms that is independent of x on both sides. Namely, if you open up the numerator functions, you get an x term that has a coefficient of only a. The term that is independent of x comprised of 2a plus b. You can compare the left-hand side and the right-hand side equations to establish the fact that the coefficient to the term x on the left-hand side is 6, while the coefficient to the right-hand side is just simply a. It is quite straightforward to write down the constant a is simply equals to 6, whereas the term that is independent of x is 2a plus b is just simply equals to 7. So from here, you would obtain b equals to minus 5. The coefficient of a in the partial fractions in example 13 is just simply equals to 6 over x plus 2. The constant term b in the second partial fraction terms is just simply minus 5. As a conclusion to this video, we have discussed how to perform integrations for the integrands of a proper fractional function, where the functions comprise of a repeated linear factor in its denominator. The fractional functions is decomposed into two partial fraction terms. The first term is a over x plus 2, while the second term is b over x plus 2 squared. Once the fractional function is decomposed into its corresponding partial fractions, the constant a and b in the partial fractions can be obtained by comparing the coefficients to the x term and the term independent of x on both sides of the equation. Then the integrations of the fractional function is equals to the sum of the integration of each partial fraction terms. Both of the integrations of the partial fractions can then be carried out to give you the full solutions for the integrations of the fractional function.